All right, welcome back to our next video. So we're continuing from part one. All right, so B2 now, we're supposed to draw the displayed formula of compound P. So if you remember, compound P it was C2. Compound P, it was C2H6. All right, so that was just it. Write the displayed formula, which is C2H6. All right, so the next part of the question now, it is asking us to outline the mechanism for the reaction of P with liquid bromine using appropriate notations and equations. So we know that compound P is an alkane, and so it will undergo free radical substitution. And we know that that mechanism, it consists of three stages: initiation, propagation, and termination. So in initiation, we know that free radicals will be produced. So let us start with initiation. In the should of the bromine, the Br bond, it will be broken homolytically. So we use fish hooks to transfer one electron to each of the atoms. Remember, we need UV light for this step. All right. And so remember now, when a bond breaks homolytically, each of the atom gets a pair of electron. All right. So these are the, all right, so that is one electron, and that's the next electron. So in initiation, whichever halogen, say if it was chlorine, it is this, the same thing will occur. The bond breaks homolytically. Right, so as the notation, you would mention that the bromine to bromine bond breaks homolytically to form these two bromine radicals. So you would first write initiation, then you do this equation with the fish hook. So remember, it's a mechanism. So you put the fish hook, all right? And we mentioned that the BR bond is broken homolytically, and we get the two BR radicals. Now for step two, which is propagation, right? And for propagation, we say that free radicals are consumed and new ones are generated. So we are starting with the free radicals from the initiation step. which is the bromine radicals. They are very reactive species, and so they are going to attack the alkane molecule. In this case, it is ethane. So again, it's a single electron, so we draw a curved arrow. And to represent this attack, you simply draw the curved arrow. Not a curved arrow, a fish hook. What is going to happen here is that this carbon to hydrogen bond here, it will break homolytically as well. So remember, carbon and hydrogen, this bond is non-polar. If the bond is non-polar, it breaks homolytically. All right. And so hydrogen all right. So these two fish hooks are pointing towards each other. That means the bromine and the hydrogen are forming a bond. And then the next electron from this bond will go to the carbon atom. So let's look at what happened here. The bond between carbon and hydrogen was broken. Carbon got one electron from the bond. So that means on the product side, we should have the carbon, this same alkane, however, it will have one less hydrogen atom. So remember now, this hydrogen is no longer attached. Also, remember, the bond is broken homolytically. So the carbon atom, it got one electron. And this hydrogen and this bromine are forming a covalent bond. One electron from bromine and one electron from hydrogen. So we get a molecule of HBr. Right? Now, propagation has two steps. So the first step is where the bromine radical attacks the alkane molecule. In step two, well, this is now an ethyl radical. If you want to say alkyl radical, it is going to attack a Br2 molecule. All right, so as we said, in step two of propagation, the radical now is going to, the alkyl radical is going to attack this bromine molecule. When we use the word attack, it is simply looking to form a bond. So this radical is going to form a bond with this bromine atom. Just like this bromine atom, it was forming a bond with this hydrogen. Now, if you were not sure or did not understand fully this mechanism, and they are wondering where this bromine molecule come from, and we just start out with one here. I have to remember this is just representing the process. If I carry out the reaction, it would be in a container. In that container, you would have a lot of bromine molecules, not just one. So I just put 3 here to let you know that in your container, if you were doing the reaction, you would have a lot of bromine molecules, a lot of whichever alkane you're using, all right? So you have a lot of everything, not just a single molecule, all right? Just to clear that up. All right, so as usual, we're going to draw our fish hook. draw it a little better. All right, have to work with that. All right, so again, this bromine to bromine bond here, it is going to be broken homolytically. It is a non-polar compound. So one electron goes to this bromine, right? And the next one is going to this bromine atom here. But remember, this electron and this one from carbon, both of them are being used to form a covalent bond. So on the product side, you will now have bromoethane. As you can see here, the covalent bond between carbon and bromine has been formed. So here we show the two electrons being shared basically. All right. This bond was broken homolytically. This bromine atom, it got a single electron here. And so we have a bromine radical. So as you can see, one free radical is consumed here, new one is produced. All right. So that is what happened in the propagation step. Right, so the key thing that happened is that the bromine radical, it attacked the ethane molecule to give the ethyl radical. And then in step 2, the ethyl radical attacked the bromine molecule to generate a molecule of bromoethane. So in the final step now, which is termination, as it says, free radicals combine to form a molecule. So we are just going to combine the free radicals randomly. So two bromine radicals can combine, two ethyl radicals can combine, and a bromine and an ethyl radical can combine. All right, so here are the three termination steps based on this example. So so as we said, free radicals combine. So two bromine radicals to form the molecule. Remember, a radical is any species with an unpaired electron. All right. Two ethyl radicals would combine to give you a molecule of butane, an ethyl and a bromine radical to give you bromoethane. Right? Remember, you would write this heading and what happens, and then you will do these three steps. Likewise, you would write propagation above these two steps, right? And initiation above this step. Right? So that is it for part 3. There was a part 4 to the question. It asked for the name of this mechanism. And as we should know, it is free radical substitution. Okay, so for part C now, it gives us butene, so compound Q, acyclic hydrocarbon C4H8, so that is butene, and it is asking us to write the displayed formula of two isomers, but I've drawn out 3 of them. Notice it says structural, so we could not do geometric isomerism as that is a stereo isomer, all right? So for the first structural isomer, I did 1 butene. The second one is 2 butene. Because remember, you can have positional isomerism, so just move the position of the double bond. So 1 butene, 2 butene. And then to get the third one, we would remove a carbon atom and place it on the middle carbon. So you could have 2 methyl, 1 propene. There should be a next dash in there. Right, so there are 3 possible isomers So you only need to draw two. Then for part two now, it says state whether compound Q exhibits geometric isomerism. Now, of these three compounds, butene, this is the only one that shows geometric isomerism. So if you are done this, or if you were doing this, and you draw one butene and 2-methyl propene, 2-methyl, 1 propene, your answer here would be no. Right? So if you draw, let's say you did 1 butene and 2 butene, then compound Q is a yes. All right, so state whether compound Q, well, even if you did not draw it, right, you should know that compound Q, so it wasn't referring to the two structures that I drew, because all it said was state whether compound Q exhibits geometric isomerism. So you should know that even if you did not draw butene, 2-butene, you should know that or test it out to see if it shows it. All right. So remember now, geometric isomerism, it's cis strands, right? So that means, so let us look back at cis strands isomerism. To know if it has cis strands isomerism, you are going to locate the carbon atom of the double bonds. So let's start with 1-butene. All right, so let me just pause here. So for geometric isomerism, this is 1-butene, right? So the first thing I have to do is locate the carbon atoms of the double bond. And you write it like that. Then you draw 4 slant lines. So you write the carbon to carbon double bond. So the cis strands arrangement is that you draw diagonal lines from the carbon atoms of the double bond. And then you put whatever was attached. So after this carbon of the double bond, you have a CH2 group here. So all of this is a group. And the hydrogen that would be here is a group. So here you have the hydrogen and you have the ethyl group, CH2, CH3. And then this carbon atom of the double bond, all it has attached, well, this should not be there. All it has attached are 2 hydrogen atoms. No, this cannot be cis and trans isomerism. Reason being, both carbon atoms of the double bond, they must have an atom in common. Well, both of them have a hydrogen. However, this carbon atom here, it has 2 hydrogens attached to it, right? And with cis trans isomerism, the compounds are, let me look at 2-butene so we can see the difference. If you look at 2-butene here, and notice that this carbon atom, both carbon atoms of the double bond, none of them has the same atom attached. All right. So if you want cis trans isomerism, one, both carbon atoms of the double bond, they must have a group in common. So both of them as a methyl group, both of them as a hydrogen. So they must have a group in common. The reason why that is so is because in one instance, if you want to get cis isomerism, those 2 groups, in this case, the 2 methyl groups, they are on the same side of the double bond. And if you want the trans now, those same groups must be on opposite sides of the double bond. So when you look at butene, you have these 2 methyl groups on the same side of the double bond, right? These 2 are on the same side of the double bond. So that is cis. And down here, there are across from each other, right, on opposite sides. That is trans. All right, so a particular group, a specific group, they're on the same side and then on the opposite side. Now, if you look back at one beauty now, this carbon atom has has hydrogens attached. So at no point in time will you have the hydrogen atoms being across from each other. It has two hydrogens, so it cannot be cis or trans. It must have two different groups on it. All right. So because it has two hydrogens on it, it cannot be cis-trans isomerism. All right. If you should look at these two again, you will see in one instance, the same groups are on the same side, and then that same group is on the opposite sides. You do not have it here. Two hydrogens would be on the same side in each case. All right. So two hydrogen atoms would be on the same side, even if you flip. So CH2, sorry, CH2, CH3. If you bring it down, you would have hydrogen up here. Hydrogen would still be up here, and hydrogen would be here. So again, this would have two hydrogens on the same side. That would be cis. Two hydrogens on the same side, it would be cis again. All right. So for that reason, it cannot be geometric isomerism. All right. So as the question said, state if it exhibits geometric isomerism. The answer is yes. And two reasons. All right. So the reason here, the carbon atoms of the double bond both as a methyl group in common. All right. So they both have a methyl group, which means that at some point they will be on the same side of the double bond, and in other butene molecule, they will be on the opposite sides. Good. So for that reason, you can have cis and you can have trans. The second reason, the double bond does not allow the molecule to be, or the atoms to be rotated. So this carbon atom, it cannot be rotated. So the carbon to carbon double bond prevents this methyl group from coming down here. So you cannot spin it. All right. So if it is in the cis configuration, it will stay as cis. And if it is in the trans configuration, it will stay as trans. All right. So those are the two reasons. The carbon atoms of the double bond, they must have a group in common. Second reason, the restricted nature of the double bond does not allow cis to be converted to trans and trans into cis. All right, so there is a part D, which involves the next mechanism and some more short answer question. So I will do a part 3. So I'm going to stop this here.